just looked at how mass can be distributed throughout a fluid, and that brought the idea of density. Now we're going to talk about how force can be distributed. So we can talk about force being distributed throughout a fluid or even onto a surface. A distribution of force is going to get us to the idea of pressure. So first, a pressure is a perpendicular force divided by an area. What I mean by that, if I've got a board like this, and I put a force on that, if I have a force this way, I can break that force into two components, right? I can say I have a component of that force that points along my board, and I have a component of that force that points straight into my board. This one I'm going to say is my parallel force. This one I'm going to say is my perpendicular force. So my pressure is going to be a force over area. There is then the next question of what area are you talking about? Well, whatever area the force is acting on. So if I've got a board like this, and let's say this is the line vertical coming off of it, and then I've got some kind of a force coming in this way, I'm going to grab the perpendicular component of that force. That would be this. And then the area that I want is just the area of this board. Assuming that force is actually acting, not at one point, but across this whole thing. So if that's the case, I can find the pressure acting on this by doing the force over the area. Now force gives me units of newtons, area gives me units of square meters, so I end up with units of newtons per square meter, which I will also define as a Pascal. One Pascal is equal to 1 Newton per square meter. This is one that you'll actually see a couple different ways. You will see Pascal from time to time, you will see newtons per square meter. A lot of times, because the sorts of pressures that we really deal with are like 1 Newton per square meter, that's the force that a 100-gram mass would put out. So like 1 Newton it's not much. It's not a lot of force. And then to spread that over a square meter is actually quite a bit of space, so a Pascal is not much force at all. A lot of the times we deal with kilopascals. When we look at just air pressure, so at sea level, the pressure from the air is about 101.3 kilopascals, which might give you a sense of scale. Pressure is what's actually responsible for things like puncturing, and it's what we are actually feeling when we hold out your hand and you see how heavy is this thing versus how heavy is that thing. If they have the same surface area, if you're holding both of them by a rope or something, that'll work. But if you hold maybe like a big can of crushed tomatoes in one hand and it's 28 ounces, but you hold something small in the other hand, it can weigh less, but if it's got a smaller surface area that you're holding, it can feel like it weighs more. If you hold in your right hand this 28 ounce can, which is fairly big, and in your left hand you hold something that has, that weighs maybe 20 ounces, but it's hanging by a thin rope, well, that thin rope has a much smaller contact area with your hand, so the amount of pressure will be higher, and it'll actually feel like that's the heavier one. Once upon a time, in the early days of flight, airplanes were made of the lightest material they could make, which is still, to a point, something that we do. less excessively now, but airplanes were made of the lightest material that they could get away with, and it became a problem really early on that women flying in particular would wear high heels. It was just something that happened. But high heels, instead of having your body weight distributed over a footprint like this, now your body weight is distributed over a footprint like this. So the area of a footprint like this, maybe a size 10 shoe, that area is 38.2 square inches. The contact area of a high heel of maybe a size, let's go with a 7 shoe, works out to be only about 14 square inches. So then you can do some amount of math. You can say if this is for somebody who has a mass of, or who has a weight of maybe 180 pounds, then that's going to give a force, well, of 180 pounds divided by that area. That's going to give a pressure of about 4.7 psi. I mean, this is assuming this person's standing on one foot, but while walking around, there are moments where you're standing on one foot, right? So that's that part. Let's say this person, even if this person has a mass of, well, let's do this. Let's say for 4.7 psi, what weight would this person have to match up with that 14 square inches? So I'm going to say 4.7 psi equals their weight divided by their area. So their weight works out to be 66 pounds. Which means a 66-pound person wearing these shoes will exert as much pressure as a 180-pound person wearing those shoes. This is a problem because most adults do not have a weight of 66 pounds. Higher pressures, they start to be bad news for this really lightweight material, and it became a thing, especially early on during commercial flight. It became a hazard that someone in a high heel shoe could actually puncture through the floor, and that's a problem. So while it sounded like a very arbitrary rule early on in the days of flight, high heels weren't allowed to be worn on airplanes for this reason. Just kind of an interesting thing about what happens with pressure. So what are some things we can do with pressure? Here's an example. You can figure out the mass of your car. I'm going to copy paste a picture of a car here and show you what I mean. Let's say I have a car and then I want to figure out the mass of it. I can put pieces of paper. This is actually something you can do at home. I can put pieces of paper underneath the tires. And I can trace out the amount of space that the tires are in contact with the paper. And I'm going to do that for all four. So then I take my paper and I label. Like this is my front driver's side tire maybe. And what I see is that this much area is covered by my tire. So I just took a pencil and traced around it. I can find that area. And then I can measure the tire pressure in the tire gauge. So let's say I do this and I find a pressure of 34 psi. I'm going to have to do some conversion between psi and pascals. Psi is pounds per square inch. So I can do some amount of converting now. So I'm going to need to convert this pounds per square inch into newtons per square meter. 1 pound is 4.45 newtons. That's a conversion factor I would need to be able to do this. 1 inch is 2.54 centimeters. So if I've got 34 pounds per square inch, I'm going to go times 4.45 newtons for every 1 pound, and times 1 inch is 2.54 centimeters, but I need this conversion factor to be squared. But this would put me in newtons per square centimeter, so I need to get into newtons per meter. So I'm going to multiply that one through again. And now I'm going to get a number in newtons per square meter. I get 234 kilopascals, so 234,000 pascals. Now I measure this area. Maybe I can measure this and I get a 4 inch by 6 inch area. 4 inches, 6 inches, so I get an area of 24 square inches. I want that in square meters, so I'm going to go 1 inch, 2.54 centimeters, squared 1 meter is 100 centimeters squared, and I get 0.0155. If this is pascals and pascals are newtons per square meter, and I have this many square meters, I can multiply these together, right? If pressure is force over area, then force is pressure times area. I get my pressure times my area and I get a force out of that of 3630. So 3630 newtons. I can go through and do this for each tire, but let's say that they are about the same. Then the total force might work out to be, let's do approximately equal, 4 times 3630 newtons. That total force is 14,520. The force that I'm getting, I've got an mg going down, I've got a normal force going up. So the force that I'm getting is going to be equal to mg. So this equals mass times gravity, which means the mass of my car is about 1,452 kilograms. I'm going to check what the mass is actually supposed to be, and we'll see how well we did. Looking up the mass of my car, I get 1,338 kilograms. of curb weight. So really that 1452 is a pretty solid estimate. This was taking the one tire and multiplying by 4. And we're going to get, because the engine's in the front, we're going to get a little bit more force on those front wheels than we are on the back wheels, which means this 1452 we knew was going to be just a little bit of an overestimate. But I think that's quite good, all things considered, being that all I did was take a couple of pieces of paper.